So to finish up 7.1 today, we actually get to come up with some equations. We get to take what they give us as a rectangular equation, or rectangular coordinate equation, which if you think about what we've graphed on this guy so far, it's been like a line, a circle, basically anything of that nature. And now we're actually going to convert it into polar form. All right. So this is kind of where the, I don't want to say heavy stuff is at, but it's definitely going to be newer material. Basically, we got to find a way to turn that equation into polar form, or vice versa. Okay, so we do have a number of equations that we're looking at here today. Let's start with 6a. Write an equivalent equation using polar coordinates. So when you hear write it in polar coordinates, what are your two variables, first of all? Instead of x comma y, what was it? R and theta. Yep. So basically, instead of having a y here, we now want to have r and theta involved. Okay. So I say that because, you know, we have equations that we can use. They're the equivalencies to it. And let's go ahead and look at those. We can recall the following. X is equal to r times cosine of theta. Again, we could look at a triangle one more time. Why not? Just so we kind of fully see where all this comes from. If we had a point here up in quadrant 1, this would be your x, this would be your y, and we called that our r. Theta was the angle measure off of that polar axis. Okay, how did we go about doing that? Well, we could use our trig functions. If we do x and r, that would be cosine. Cosine of theta is equal to adjacent over hypotenuse. If we solve for x, which we are doing here, x is equal to r times cosine of theta. And that's exactly what we read up above here. So because we have this general scheme, we can use this equation now to convert. What did the y one look like? Y is equal to what now? One more time. Yep, now we use sine because y was your opposite. R times sine of theta. So we're definitely going to use these today, especially when we convert to our polar coordinates, because take a look at what we got here. We've got x equal to r and theta. Again, those are our variables that we want to get it into in terms of, so to speak. Same thing there, y is equal to r and theta. So as we look at y is equal to -3, we said that y is equal to r times theta. So r times sine of theta. We can substitute that in for y. Therefore, that's equal to -3. And now the question becomes, what does our polar equation look like? What's our dependent variable, so to speak? Well, your dependent variable is typically going to be r. So if I want to solve for r, divide by sine of theta. So r is equal to -3 over the sine of theta. We typically don't like fractions. How do we get around that here? Yep, reciprocal of sine is cosecant. So r is equal to -3 times the cosecant of theta. So once again, just so we know what we did here, we've taken the rectangular equation, rectangular coordinate equation, and now we've come up with a equivalent polar coordinate equation using our r and theta. And we use it with our equations and substitutions. Let's go ahead and do another one. We got y is equal to x squared. Again, got to get rid of y, so I'm going to go ahead and substitute that r times sine of theta in for it. And I want to get rid of x, so I need to substitute r times cosine of theta and square all of that. R times sine of theta. I'm going to distribute that squared portion of it so the parentheses can go away. What did we want to solve for again? R. So I'm going to do this. I'm going to divide by r. we're essentially getting it, we got one on each side, so let's move it to one side. We're going to move it to the right. Cancel, cancel, cancel. One of those r's is gone. So now we got sine of theta is equal to r times cosine of squared of theta. So this is good. Things are looking out for us. R is on the right hand side now, so let's get rid of this cosine squared by dividing by the cosine squared of theta. And thoughts on how we should simplify this? There you go. So let's go sine over cosine, because I think we know that reciprocal ratio. And then we'll say that's times 1 over cosine of theta. Sine over cosine. Yep. And 1 over cosine. There you go. So our final equation is r is equal to the tangent of theta times secant of theta. And I think before we go any further, why don't we go ahead and let's take out our graphing calculators. Yeah. And let's see if, first of all, how do we do it? And then second of all, did it work out for us? Did it kind of map up to what it should be? Go to your scratch pad. Use the calculator toggle button if you need to go to your graphing setting. We're going to go to menu. We're still going to go to graph and entry. But now I'm not typing in a typical function that we normally do for our rectangular, but now we're going to go down to polar, so 5. And notice the setup right away. R of 1 of theta. Notice it always used to be y of x or f of x function notation. Okay, there we go. Now we're better. Since it's polar, now we got our r and our theta. Okay, coincidental? I don't think so. Let's go ahead and type in the first one. Let's go to what we did for 6a, and let's type in -3 cosecant of theta. Oh, do you have your calculators out of test mode? Okay, so you should be able to do cosecant. So -3 times trig button cosecant. Has everybody found theta? Theta is way down here by your pi button. It's like your pi catalog. And then arrow over to the right. So it's got some symbols down there for you if you ever need them. And there we go. Now let's kind of make some sense of it. What was the original line of y is equal to -3? Straight line, horizontal line, going through that value of y is equal to -3. And sure enough, when we type in -3 cosecant of theta, when we're in our polar coordinates, we get the exact same horizontal line going through -3. So they match up, which is a good thing. It's good. You can go ahead and type in the second one if you want to. Play around with it. Now we'll type in tangent times secant. Careful with your parentheses. Well, one more time, if we go back to it, the original equation in rectangular form was y is equal to x squared. What's that? Parabola, right? Going through the origin, and sure enough, as we plot that polar equation, there it is again. Parabola going through the origin, just like we know it. What's that? Go up to mode and go into radian mode. There we go. Good. And just like that, they switched, right? They're looking like that. There you go. So yeah, make sure you're in radian mode. Questions on that? So yeah, rectangular coordinate equation, polar coordinate equations. Let's go ahead and finish the notes. We're going to 7. Now they give us the polar equation form, and now we want to convert that back to rectangular coordinate. Let's recall some of our formulas there. Anybody remember what r was equal to? Or what we used to get r? Yep, think of your triangle, Pythagorean theorem. R was your hypotenuse. So r was equal to the square root of x squared plus y squared. So we got that equation solved for r in terms of x and y. And now I need theta. What did theta look like? Inverse tangent of y over x. Again, an equation solved for theta in terms of y and x. So we've got r is equal to -3. This one can be kind of tricky. I guess also note, I wrote the r is equal to the square root of that, but sometimes it's just best if we don't square root it. Let's just leave it as x squared plus y squared is equal to r squared. So typically when you have a polar equation where it's just r, okay, we want to use this guy. So basically what we're going to do is we're going to square both sides. Sounds kind of funky. Why would we do that to begin with? But the reason we do that is because now we have our substitution. Now I can replace that r squared with x squared plus y squared. And let's talk about this guy. What's that in rectangular? Anybody? It's not an ellipse. We can rule that one out. And for gosh sakes, it's definitely not the hyperbola. Boy, let's not bring that one back, right? How about the circle? X squared plus y squared equals that r squared. This guy is a circle. Can you recall what your radius is? Yeah, 3. So there you go. Circle. And let's just think about this for a moment. What did r represent when we were doing polar coordinates? The length, the radius, the distance from our pole, right? Or from the origin, okay? So if you think about this in a sense, when you define an equation, it's really the set of points that satisfy that equation. So we are looking at the set of points that happen to be 3 units away from the pole or the origin. So we could say this point, we could say this point, that point, and that point. Now you might be saying -3. Okay, you're right. So instead of plotting this point, I go across and I plot that point, right? So we're getting all of them anyways. But then that point is 3 units away, 3 units away. And if we get enough points, they fill in and we've created our circle. Okay? Radius of 3. So if you see r is equal to a number, just know it's a circle with that radius. Let's go ahead and move on. Theta, pi over, or -pi/4. Okay? We could go back to, how do I want to do this? Oh, we could do it that way. That's fine. We could take the tangent of both sides. Did you know that was a legal move? Just like you can multiply both sides of the equation by 2 or whatever your favorite number. Now we can take the trig function of both sides. And the reason I want to do that is because, again, if we create kind of our list of tools over here on the right, you can add this one if you want to. Tangent of theta is equal to y over x. So if you haven't figured it out, these are really important. These are like your go-to equations that you're looking for substitutions for. Okay, so I'm going to use this guy down here. And I wanted to get one side of the equation to be the tangent of theta. And now that I have it as the tangent of theta, I can use my substitution. I've now got y over x, so I can replace that tangent of theta with y over x. And can I evaluate the tangent of negative pi over 4? Let's go to our unit circles. Negative pi over 4, down there at 7 pi over 4. We take the y over the x, what did we write there? I think it's negative 1. That middle one. There you go. So we substituted here on the left, evaluated here on the right. We just, again, can go to our unit circle, find negative pi over 4. X and y are the same, except one of them's a negative. I think your y value is negative, so it's negative 1. Alright, and anytime we solve these equations, typically if it's a line, which it is here, we want to solve for y. So we'll multiply both sides by x. Let's go ahead and do that here. Multiply by x, multiply by x. And again, I'm hopeful that when you're all done, you kind of see, hey, it's an equation that I can recognize. All right, this has a degree of 1, so it's a linear equation. Slope is negative 1, going through the origin. All right, let's make the connection there. So if I draw that, y is equal to slope of negative 1. There it is, just like that. Our original polar equation, theta is equal to negative pi over 4. Where was that angle at? Down on your unit circle. Well, it's down there in the bottom right hand corner at 7 pi over 4. Isn't that the exact angle? So you drew the line that mapped right onto that angle. And then how it works is, okay, I know it's supposed to go from here to here, but that line does go in the opposite direction. It can go that way too. Okay, so the line fell on the angle that it originally gave us. A couple more. R is equal to 6 times secant of theta. This one we started a little bit different. You know, secant's all fine and dandy, but again, if I want to get this thing into polar equation, I do know that cosine and sine are some equivalencies that I have. I really don't have secant and cosecant. So I know I created a fraction here, but I have my cosine, which is good. And now what we're going to do, multiply both sides by cosine. R times cosine of theta is equal to that 6. And what was R times cosine of theta equal to? Yeah. What's x equal to 6? Vertical line. Obviously going through 6, you know that. Last one, R is equal to 6 times sine of theta. Alright, so we do have sine now, so we don't want to divide or use the reciprocal. Again, this is kind of it takes time to catch on to it. R squared was always a good thing for us, right? We want to get it in terms of x and y. So this one, again, kind of like the first one, we ended up squaring it. We want to do the same thing here. One more time, let's go back to the directions just so we're all on the same page. Write an equivalent equation using rectangular coordinates, which means which two variables do we want to see in our equation when we're all done? X and y. So once again, the goal is to get rid of the theta and the r, and I want x and y to appear for us. Okay, let's see if we can do that. Well, r squared, we had that equivalency. That's really good. That gets us x and y. So left-hand side is x squared plus y squared. Over here on the right, we got 36 times sine squared of theta. Thoughts on what we can maybe do there? I can, but unfortunately, I realized I had mixed up. We really shouldn't have said squared. The left side is fine, guys. But I shouldn't have said square both sides. Instead, we should have multiplied by r. Which you might say r times r is r squared. Yes, that's all good. My bad. We're going to multiply both sides by an r. And there's a reason why we do that. We need to change that 36 to just a 6 again. We'll get back on track here. 6 times sine of theta times r. I'm going to rewrite this just so you can see it, and I might even put it in parentheses. Again, the only thing I can tell you is know what you have available to you. I had sine, so if I can get an r times sine of theta to appear, then I can replace it with a y. And that's what we have here, r times sine of theta. It's just y, so 6 times y. I'm going to subtract that to set it equal to 0. Technically, this equation would work, guys, but we're going to take a minute. We're going to tie this thing in a nice bow. If I got x squared and y squared involved, what type of graph are we looking at again? Circle. And remember, with the circle, it was really nice if we could have like x minus h quantity squared, y minus k quantity squared equals r squared. That was the equation of our circle. So if you gave me this, I would probably take it. Maybe I'd take off a half a point or a point. But if we want to get it into this form, oh boy, skill that you guys love. Completing the square. So hang with me. X squared plus y squared. Half of negative 6 squared. Well, half of negative 6 is negative 3. 3 squared is 9. Plus 9. What we do to one side of the equation, we got to do the other. So plus 9 over here on the right. We're about there. The x squared doesn't have a single x, so you can leave that as x squared. Okay. This one does FOIL for us, or factor, excuse me. Y, 3, 3, minus 3, minus 3. And in a very ugly fashion, we'll write it over here on the right. And there it is. X squared plus y minus 3, quantity squared equals 9. Let's take a moment. I know we're about out of time already. Let's go to our graphing calculator and see if we can get this thing to show up for us. R is equal to 6 sine of theta. We got R and theta, so polar form. So 5. And actually, I need to think for a moment.